Let's start things off by addressing a pretty relatable misconception in modern AI. There's this lingering idea out there that if you want to build a smarter system, you just need to build a bigger, monolithic, single model. But as we're seeing, scale definitely has its limits.
Think about it. What happens when a problem is just way too complex, or maybe requires too many specialized steps for a single large language model to actually solve reliably? Well, by the end of this explainer, you're going to understand how distributing those workloads across specialized AI agents completely solves this single agent bottleneck.
You see, a single agent operates in total isolation. It takes a prompt, does its absolute best, and hands back an answer. But a multi-agent system takes a fundamentally different approach. It uses a distributed network of intelligent entities, and they all work collaboratively toward one shared goal.
So, formally speaking, a multi-agent system, or MAS, consists of multiple autonomous AI agents collaborating within a shared environment. And why do we even build these? Basically, they're designed to drastically improve accuracy, adaptability, and scalability, all through pure specialization.
To really build our intuition here, think of a single agent like a solo developer. Imagine this one person trying to build a massive enterprise-grade application entirely alone. They're trying to write the code, run the QA tests, deploy the infrastructure, and manage the database. Now, they might be absolutely brilliant, but eventually, they're going to make mistakes, lose context, or just plain burn out. That right there is the single agent bottleneck.
Now, a multi-agent system solves this by functioning exactly like a structured engineering team. Instead of one person doing everything, you break down that massive goal into agent-specific subtasks. So one agent acts as the front-end developer, another tackles the back-end, and a third acts purely as a QA tester, just to double-check everyone's work.
And this is exactly why a multi-agent system consistently outperforms going it alone. It unlocks a much larger pool of shared resources and allows for really deep task optimization. Plus, the agents actually share their learned experiences with the rest of the team. That prevents repetitive learning from scratch and highly optimizes the overall efficiency of the system.
Section 1. The mechanics of coordination. How agents actually communicate and execute. Let's ground this technically and see how these agents coordinate under the hood.
Essentially, every multi-agent system relies on three fundamental components. First, you have the agents themselves, which are your autonomous decision makers. Second is the environment, basically the shared workspace or context that they operate inside of. And third, you have the communication protocols. These are the strict rules dictating exactly how the agents are allowed to interact.
So, what does the operational loop look like for one of these agents? Well, first, the agent perceives its surroundings or any incoming data. Then, it reasons about that data, usually using an LLM as its core cognitive brain. Based on that reasoning, it executes an action. And finally, it interacts with the rest of the group to share what it did.
Now, to execute that loop, agents obviously need to talk to one another. They use those communication protocols we mentioned to pass structured messages back and forth. In practice, this is often done using standard JSON payloads or specialized agent communication languages like FIP-ACL, which structure an agent's intent into super clear actions like request or inform.
When you're architecting these systems yourself, you typically choose between two network types. Centralized networks rely on one central unit overseeing all the data. That makes communication pretty easy, but it definitely creates a single point of failure. Decentralized networks, on the other hand, allow agents to share information directly with their neighbors. This gives you incredibly robust modularity, but it makes coordination a whole lot more complex.
And because that coordination gets so complex, modern orchestration frameworks have stepped in to help. Tools like CrewAI, LangGraph, and AutoGen are specifically designed to manage these agentic workflows. They make sure your agents are called in the exact right sequence and that the whole graph of interactions flows smoothly toward your final goal.
Section 2. Mass in Production. Real-world AI agent workflows. Let's shift gears and look at where this stuff actually lives in the real world, and why practitioners care so much about it.
Out in production, these systems are actively automating some incredibly complex, multi-step workflows. For example, in software development, you might deploy a framework where one agent just writes code, a second analyzes past bugs, and the third purely runs tests. Splitting up those roles drastically reduces LLM hallucinations compared to just using a single prompt. Or look at supply chains. Virtual agents are acting as inventory trackers and negotiators, literally adjusting operations in real time based on dynamic constraints.
So, to bring it all together, A multi-agent system fundamentally transforms AI. It takes it from being a solitary oracle trying to do everything and turns it into a dynamic, highly specialized team.
If you take away just one thing from this explainer, let it be this. When you are solving complex engineering or business problems, distributing the workload across a team of specialized AI agents will absolutely always scale better than relying on a single, isolated model.